In today's video, we're going to discuss what's known as the position representation in quantum mechanics. And it's going to be a little bit of a switch of gears. We're going to kind of be coming at these topics sort of from a different viewpoint from here on out. Well, we'll use both, but we're going to introduce a sort of separate view today. And hopefully we can get comfortable with that by the end of today's lecture. Recapping to date, though, what we've done in the course is we first just kind of introduced the weirdness of quantum mechanics using the spin 1/2 system and Stern-Gerlach experiments. We then sort of built up this formalism of dealing with those things where the state of a system is described by some state ket or some state vector existing in an appropriate Hilbert space. We went through the Dirac notation with kets and bras and operators and eigenvalue equations with those. We also looked at the matrix representation of those equations and basically built up and introduced the 6 postulates we talked about in the book. We also talked about measurements and how they sort of collapse into one of the basis states after a measurement. And we also looked at commutation and compatible observables. And then we finally finished up with time evolution. And we used the example of spin precession and Rabi flopping, but basically Schrodinger's equation, and solve that. The chapter 4 was kind of separate, just looked at some really interesting kind of quirky things associated with quantum mechanics, in particular this sort of spooky action at a distance that Einstein sort of came up and discussed, and then Bell's inequalities showed the true sort of weirdness of what was going on there, as well as the Schrodinger's cat Gedanken experiment. What we're going to do now, this sort of approach I really like, is what's called the spins first approach. You know, it's kind of a newer way of teaching quantum mechanics where we start with this sort of system, and I think it really gets at the heart of what quantum mechanics is and how it works. But it's not sort of the traditional approach. Traditionally, quantum mechanics is taught starting somewhere completely different, and that's where we're going to start. You know, today it starts. Typically, the courses will start with the position representation, and it follows sort of historically what quantum mechanics is used for is sort of trying to describe the microscopic structure of systems, particularly what are the allowed energies of a system. If you think of just, for example, time evolution, you know, the way we approach that, we had phase factors that were, you know, based on the eigenenergies of our system, and we expanded our state vectors in terms of the eigenvectors. So we haven't actually talked about how do we know what those things are, and that's sort of what we're approaching now. The sort of experimental way that we typically come about finding these things out is spectroscopy. So you might remember labs like this from Physics 203 or your modern physics course or some previous course maybe. But if you haven't, really quickly, what we're looking at here is a lamp here that's filled with some gas, you know, some element, say neon, hydrogen, whatever, and it's excited with a voltage so that all the electrons on that atom get excited and relax, and they emit light, and it shines into this diffraction grating, and we have sort of a microscope or lens here that can measure the angle that light is bent at. So we have a lamp. It's outputting a bunch of light that correspond to the energy spectrum. Shine that through a prism or a diffraction grating or something that has some wavelength dependent splitting. That light spreads out according to its wavelength, and we use this to measure the angle that light deflects at. And from that, we can kind of pull off the wavelength of that light. Now, bound systems like atoms, where we have, you know, an electron is bound to be close to the nucleus. They're stuck together. It limits their motion in that a bit. They have essentially their spectra are like fingerprints, right? The lines and the energy levels correspond to that system, so we could use it to identify things, what types of systems there, and it corresponds to the transitions between the allowed energy levels. So if you had performed this lab in the past, you would basically be measuring a wavelength, and we know that the energy associated with light is Planck's constant times its frequency. So the frequency of light we're measuring is corresponds to a transition between energy levels. So the frequency is the difference in those two energy levels divided by Planck's constant, and we can get that frequency and relate it to a wavelength just because the wavelength is equal to the velocity of a wave divided by its frequency, or in this case, the speed of light divided by that frequency. And we get this, that the wavelength of the light we see is equal to Planck's constant times c divided by the energy splitting of the levels that that electron transitioned through. And you hopefully remember from that lab or modern physics the certain types of transitions we get in, say, the hydrogen atom, where we have these quantum numbers, for the different energy levels, any 1, 2, 3, 4, 5, 6, all the way up, and we can have electrons transition from a higher energy level down to the ground state. It's called the Lyman series, or they can drop down to the second state. It's the Balmer series, the Paschen, the Brackett, all these different transitions. Turns out the Balmer series are right in the visible spectrum. So if you did that lab, that was probably what we were looking at. But again, we measure those lines or the emission spectra from that lamp. And from those wavelengths, you can determine the energy splittings and sort of deconvolve out of that what the energy levels are. Right, so experimentally, we do spectroscopy. You can also do absorption spectroscopy. You can do tons of different kinds of spectroscopy where you're essentially probing these systems and looking at transitions between levels and trying to pull out what those energy levels are. How does that, other than getting those numbers, how does that help us understand how things work? Well, we need some theoretical understanding of where do these energy levels come from? Why are they at those energies? And to do that, we have to determine, we have to solve for the eigenvalue equation for our energy operator. So you remember our Hamiltonian is our energy operator, and the eigenvalue equation looks like this. So we've mentioned previously, and if you took Physics 320 with me, or maybe another advanced classical mechanics course, the Hamiltonian can be written for natural systems anyway as the kinetic energy T plus the potential energy. It's essentially just the total energy in classical mechanics. The kinetic energy is 1/2 mv squared, or if we want to write it another way, that can be mv squared divided by 2m, which is just the momentum squared over 2m. The potential energy, that's going to be very system dependent, depending on what forces and interactions are there. But the only thing we really know is that can only be a function of position, right? So we have some potential energy that's a function of position. So our Hamiltonian, written with the kinetic and potential energy that way, looks like this. We're looking at quantum mechanics, though, and that eigenvalue operation. So this Hamiltonian has to somehow be an operator. It's operating on our state ket. So typical notation is putting this little hat on top of operators to distinguish them from just different variables. And that Hamiltonian is the momentum operator squared divided by 2m plus the potential energy as a function of the position operator. So the question then becomes, all right, if we're going to look at this and try to solve it, what are those momentum and position operators? How do they act on our states? Well, to sort of deal with these, we're going to have to switch representations, right? We don't want to use the representations we're used to. But if you think back to our spin 1/2 system, the representation we used most often, was the z basis, right? Where you could write a general spin state in terms of a linear combination of those spin eigenfunctions, right? Where we had just exactly what I just said. The general state ket was some constant, which was the projection of that wave ket, the projection of the state ket onto the spin up state times the spin up ket plus the projection of that state ket onto the spin down bra times the spin down ket. Right? We want to write this state ket sort of in a position representation, which is represented by this, and typically that's referred to as the wave function. And today we're essentially going to go through what this means and try to sort it all out. In this case, the energy eigenfunctions or eigenvectors written in the position representation have their own sort of wave functions that we are going to use this notation for. In this representation, our energy eigenvalue equation becomes this, where that Hamiltonian operator is acting on our energy eigenfunctions, these phi terms, and it equals the energy eigenvalue, the energy of that eigenfunction, times that eigenfunction. This is just our eigenvalue equation. So what are those operators in the position representation? It turns out, and you can honestly take this as a postulate if you want. If you read, there's another book by Townsend, if you want to get more detail on where these operators come from. But for the purposes of our course right now and where we're at, you can take them just as on faith. But these operators in the position representation are given here. The x operator is just multiplying, the position x, and the momentum operator is negative I h bar times the derivative with respect to x. So this is, we're looking in one dimension along in the x direction. So that makes our energy eigenvalue equation this. So we've just substituted those position representations of our operators. And simplifying that, our energy eigenvalue equation is now this. And if you look at that, this is actually a differential equation for our energy eigenfunctions. And this is how we solve where our energy states, what our energy states are and what their eigenvalues are, right? This, in the position representation, our eigenvalue equations sort of translate to differential equations. Our goal is to solve those differential equations and determine what those eigenenergies are and what those energy eigenfunctions are. So what are they? And I don't mean, what are they for a specific example. I mean, in general, what are these energy eigenfunctions in the position uh, bases? What do they mean, these wave functions? Well, we can recall it in our spin 1/2 bases. We had a general state vector psi, and if we wanted to write, we could write that in that representation this way. Essentially, if we multiply it by the identity operator, which we can replace thanks to the completeness relation of the projections onto our different basis states, we get this. And in our matrix representation, we just had that column vector of that state vector projected onto each of those possible measurement outcomes, the spin up and the spin down, those eigenvalues for the basis we were representing it in. And we had the probabilities of measuring one of that in that we had the probability of a measurement outcome in that basis being this, the basically the projection of that state vector onto the spin up all squared, or if we measured the spin down all squared. Those probability amplitudes squared. So the spin up and spin down were just the eigenvalues for the operator that defined what representation we were in this case, the S sub z operator. We can analogously do the same thing in the position bases, right? Consider that eigenvector and the x operator acting on the state vector will give us some eigenvalue. If we take the completeness of that basis and replace the identity matrix with that, we can represent that as a column vector where we have x1, x2, x3, all the different possible positions, eigenvalues or eigenvectors times that state function in a column vector with the probability amplitudes and or the probabilities of measuring that state, that particle, say at a position xi, given by that probability amplitude squared, where xi are just the eigenvalues of the position operator. This already has some issues with it, all right? This is a pretty big abstraction. For starters, we have to think carefully about what we mean here. We can't measure an exact position, right? There's always some uncertainty to that, and objects, exist and they're not exactly point particles, right? There's always some spatial extent to what they exist at. So we fundamentally can't really measure an exact position. Um, to put that in sort of a more obvious ways, let's consider there's a probability of measuring some particle at position x1 that is greater than 0. So we measure a particle and we see that at x1 there's some probability it's there. We can always pick another position x2, some small distance delta A away from x1, such that it's close enough that the probability there is also greater than 1. However, since there are infinite number of points between x1 and x2, this is position is continuous. Uh, it would appear that the probability at all of those points between x1 and x2 would also have to be greater than 0. And if we add up an infinite of those, it looks like the probability would be greater than 1, which is sort of a nonsensical thing to say, right? So we have to be careful about how we're actually dealing with this in this representation. All of this arises because x is continuous. And what we're used to is dealing with these discrete problems where spin could be spin up or spin down in our spin 1/2 system. Here, it's continuous. So how do we do this? Well, let's consider these probability amplitudes graphically, right? So thinking back to our Stern-Gerlach experiments, we measured the general state vector with a Z analyzer, and we got, let's say some probability amplitude of spin up, some probability spin down, square them, we got this. If we plot that, the probability as a function of the measurement outcomes, we're going to get these discrete values, relating to whatever that probability was. If we did the same thing with position, now these are probability amplitudes, we haven't squared them, but if we look at the probability of measuring the position of some particle at all of these different positions, x1, 2, 3, 4, 5, we're going to have some amplitude of that projection or that probability amplitude at those different points, right? However, this x is continuous in that, so it's not the best way to view these as sort of discrete points at each of these locations, but more of a function, right? And this is sort of the gist of what those are. This is what we would call the wave function, and it is a continuous function of x that's describing the probabilities amplitudes of measuring that system at position x, right? So those wave functions are the projection of the state vector onto that position x. It's the probability amplitude of measuring that particle or state or whatever at x. The probabilities are therefore also continuous. So rather than the probability of a single outcome, we have this probability is a continuous function of x, right? Now that we've sort of acknowledged this continuity stuff, and we can deal with that apparent infinity issue that we sort of pointed out. So we need the probability of measuring this particle to be 1, right? If we measure the position of it, it has to be somewhere, and we need a probability of measurement to be 1 if we measured over all the possible positions. However, because this is continuous, summing over all those positions becomes an integral over all positions over all space, from negative infinity to infinity. So if we integrate over that probability with respect to x, we have to get that equal to 1. That's essentially the normalization condition. And we can see just based on unit analysis, the 1 is a unitless number. It's just the total probability. So this px here isn't actually the probability, it's a probability density, right? dx has units of length in this one-dimensional case, so px must have units of inverse length, or if it was a two-dimensional problem, inverse area. If it was three-dimensional, it'd be inverse volume. So this is the probability per volume of measuring that position in that volume. And so this px dx is how we kind of interpret these probabilities. This is the probability of measuring that particle and some infinitesimal distance space between x and x plus dx, or essentially the area under the curve of this probability amplitude squared, right? So this means that if we want to determine the probability of measuring a particle between two locations, say between point A and point B, what's the probability we find the particle in that range? We just take that probability density given by our wave function complex squared and integrate it between A and B, get that area under the curve, and that gives us the probability that if we measure the position between of that particle, its outcome will be between A and B. So that's the position of the particle. We can also look at just the general probabilities and projections onto a general state. So if we have a system in some state psi, and we want to know the probability of measuring that state in some other state phi, we would take this as the probability, just the projection of psi onto phi all squared, right? We can take that inner product, that probability amplitude, and we can throw an identity into the middle of it. Multiplying by that identity operator doesn't change the ket it's acting on in any way. Completeness lets us write that in identity operator in terms of our position bases. If I take that sum just outside of that bra and basically pull in the bra and the ket into the sum, I get this, and those, it's continuous, so that sum's going to become that integral, and that phi x inner product and that x psi inner product, those are what we defined as the wave functions for those states, or the complex conjugate for the case of the phi state. So that probability amplitude of measuring psi in a system in state psi and measuring the outcome of the system being in state phi is just going to be the integral of the two wave functions over all space, and then complex squaring that whole integral. So you get essentially the wave function overlap of those two states, integrate over all of that, and then square it to get that probability. Putting this all together and just sort of mapping our, what we're used to as Dirac notation into our position representation, we can do this. Starting with our normalization condition, all our state vectors are normalized so that their inner product equals 1. In the position representation, this amounts to, if we integrate over all space the product of that wave function with its own complex conjugate, we must also get 1. We write kets in terms of the corresponding wave functions, bras in terms of their complex conjugates of those wave functions. If we take, any inner product of two of those wave functions, it essentially amounts to integrating over all space. And operators simply become some spatially continuous operator. We saw that x operator just becomes x, and the momentum operator had a derivative with respect to x in it. We can now, using those tools, we can look at expectation values. So if we wanted to know the expectation value of some observable A previously, we would just sandwich the bra and ket for whatever our state of our system is in there. If we take that A operator and operate on that ket, that's going to be the equivalent. Basically, we're just converting these all into the position representation. So that bra becomes the complex conjugate of the wave function describing that state. The operator becomes the operator in the position representation, and the state ket becomes that wave function. And because it's in those bra ket notation, we integrate over that all space to get that expectation value. So, for example, the expectation value of a position x, we just take the complex conjugate of the wave function, the position operator, and then the wave function itself, integrate that over all space, and that gives us our expectation value. Because x is just some variable x, we can pull it outside of those two wave functions, and we get just that complex squaring of the wave functions. If we look at the expectation value of momentum, we do the same thing. We just put that momentum operator in the position representation between the complex conjugate of the wave function and the wave function itself and integrate over all space. That momentum operator is negative IH bar ddx. And so we can't actually go any further than this. We can't pull that out because it actually has to operate on that wave function. It's not a scale. It's not some variable like x was. It actually is performing an operation. So recapping everything, we've got, hopefully we've sort of got to the point where we're familiar with our Dirac notation from what we've covered so far in the course. What we've done today is sort of discuss how to map that to the position representation and the concept of a wave functions. And the goal that we're going to do moving forward for the next few videos and the next few chapters is use that to sort of solve our energy eigenvalue equation in the position representation. And if we can solve this differential equation, we end up knowing the energy spectra, i.e. the values of the possible energy states, or the energies that are allowed for that system, as well as the wave functions for those energy eigenstates. Next class, we'll go into we'll start with some specific examples, in particular the particle in a box problem.